Ladyada.
Hey everybody, and welcome to my desk. Happy Sunday, everybody. Hope you're having a good weekend. Yes, this week at my desk, we're doing, we're still trying to get that hardware pump primed full of good designs. You saw I did a lot of prototypes, and now I'm kind of like trying to get some of those out into the world. So this week, the product I was successfully able to test was a little constant current booster. So let's go to the overhead. So I can show you some nOOds. So these are nOOds, these LED filament, flexible filaments. We also have, fixed filaments, like these letter filaments, that you can use to spell out words and stuff. They're very cool, but a lot of people have trouble using them because they're LEDs, but they're 24 volt LEDs or 12 volt LEDs. Like these are 12 volts, and then we have longer ones that are 24. And that kind of weirds people out because they're like, well, first off, you need to get a 12 volt power supply, and to do that portably is not always easy. Most people have 5 volts USB available, but they don't have 12. And they're like, should I get a boost converter? And then what LED resistor should I use? And it's 12, and it's not quite 12, it's 11 and a half. And Carter wrote a guide about it, but I've noticed it really confuses people. So I made a little board that I think will solve a lot of these issues. It uses the TPS 61169, which we've covered before. It's a constant current boost converter, which means it doesn't give you a fixed voltage out. It gives you a fixed current output, which is different, but really useful for driving LEDs. So for example, this is it driving, nominally a 12 volt nOOD at, I think this is I think I have it on the lowest setting, which is 25 milliamps. And then if I flip a little, I have little dip switches. Now it's 50 milliamps. So you saw it got brighter. And that's how you have to drive. You have to drive at constant current, 50 or 25, not trying to guess the voltage because the voltage is going to flux and vary depending on the humidity and temperature, and also are they yellow LEDs or green or blue? And then, this booster actually, it can go pretty intense. This is, I think, 350 milliamps, which is actually kind of what it's rated for. And this is really nice and bright. It's a little bit warm, but not too much. It's running off of 5 volts. And over here, on my power supply, so I can see that the current being drawn, and it's drawing an amp. And that's pretty nice. So this little booster, look here. Whoops, I think I just shorted. Hold on, no, it's fine. This little booster, which I'll show. Hold on. Yeah, this is shortened. Hold on. Sorry. This little booster chip here has it's a 1.5 amp internal switch. It's really tiny. It just needs an inductor, a couple components. And then you can set how much current goes through by using a resistor. In this case, I have some switches. You can see a little text here to see how much current is going through. So this is good. And then, like I said, it's good for this 12 volt nOOD. But what's also nice is that you don't have to have, what's nice about constant current is if you have these LED filaments letters, for example, and let's see which side's positive. I'm going to guess it's this side. And you have a flexible number of LEDs that you want to put in, and that might change. You might have 4, you might have 12. It'll automatically do the right thing. So let me just get this so it doesn't short. There you go. So this is a nice warm 50 milliamps, right? It doesn't matter how many letters you have. They're in series. You see, I just have little wires in between each one, and I clip them in the center. So this is, I don't know how many volts it is, 3 times 1, 2, 3, 4, 5, 6, 7, 8. So, it's about 24-ish volts, maybe 25, maybe 22, but it doesn't matter because constant current is good for it. So this design got done, which is great because I think it'll be really useful for people with nOODs. They want to glow up, and then, terminal block, input, output. And then there's a PWM pin. If you want to PWM it, you can use a microcontroller and have it dim. But otherwise, you just wire up whatever you want, flip the switch, and you're glowing. So that's good. So that's one design that got done. Another design that didn't work out, I don't even think I have it here. I think I tossed them all, is that ideal diode, the LM73100. I blew up every single one of them, which is actually kind of cool because that doesn't happen too often. So if you go to the computer, I made, you know, it's a bummer because it's like an ideal diode, and like usually like there's not that much going on there. But I think that I had some pull-ups on the enable pin. I think you're not actually supposed to pull it up. I think it has to be a resistor divider. And like looking at the data sheet, it was like, oh yeah, there's like, you know, maximum voltages. So I put another resistor here so that the enable line isn't just pulled up. It's actually a resistor divider. See, it's like there's a divider here. And the divider makes it so the voltages, you know, you're supposed to be able to limit it. So it's like the ideal diode works between like 3 and 23 volts, but you can limit it to only work between like 9 and 14 if you just want like, you know, 12 volt approximately. But I just made it so that the resistor divider works throughout the full range. And then I also put a filter on the slew pin, which like, I don't know if this is necessary. I might remove this, but this, I was noticing, you know, power and it would like pop instantly. And often it could be that, you know, you don't know what it is. It could be that enable pin, or it could be that there was too much inrush current. And I did notice in the data sheet, they're like, oh, watch out, too much inrush current. You could have issues with pin thermal stability. And I'm like, okay, cool. I'll toss in a filter. So this slows it down, I think, to like half a volt a millisecond, which is still plenty fast. So it's like you'll get to 20 volts in 10 milliseconds. That's slow enough, maybe that'll slow it down. We'll see. So I ordered new PCBs with this design. So it's like sometimes, you know, like this Rev A of the TPS 61169 works out of the box perfect. You know, it's like because I've used the chip a bunch of times, I kind of knew like what I was, you know, what the layout, the parts, you know, I'd already figured out this component. But when you're dealing with a new component like this, you know, there's like, you can read the data sheet, but it's like you don't necessarily know what is important in the data sheet and what isn't. It's actually, you know, ironically, one of the things that it's like I was talking to, we'll have the video. I was talking to the CEO of Microchip. Was that this week? I don't know.
When did we talk to him?
Yeah,
we talked to him. Yeah, it was this week.
It was this week.
And we've already got a lot of information to their team, and we just have to make sure that the order, and we post stuff. We have a lot of neat stuff to share. And you had an amazing conversation.
We had a chat, but we talked about like
great.
He's because you know Microchip, they do hardware. And he's like, oh, totally, like, you know, LLMs and AI can do coding, but you know, the big question for a lot of electrical engineers, and he's an EE, is can they do hardware design? And I was trying to say like, well, they're good at text, and like hardware design is like more graphical, and also like the data sheets are like full of lies. Like, I think I talked about like a couple weeks ago, I was doing the OPT 4048 driver, and I was using the LLM to help me write the driver because it's a very monotonous work of like, now this register getter, now that register getter, and then shift the bits. It's like very boring. And there's like a lot of comments and a lot of, you know, repetitive code, which I'd copy and paste, but then I'd make typos. So the LM is really good at that because it doesn't make typos the same way humans do. It makes mistakes, but not the same kind of mistakes. And what's interesting is the data sheet had a typo in the CRC. And like they didn't fix it for some reason. And like I found, you know, because I was having a lot of trouble getting the CRC working. I was like, why is LLM really struggling with the CRC? Like, and then I realized there's a typo in the CRC calculation where it was referring to itself. And the data sheet, you know, the minute I looked at it, I was like, oh my God, this is obviously wrong. But an LLM doesn't know that. LLM was like reading it. It was like, well, it must be right. The CRC must CRC itself. And it's like, no, that's not technically possible. So it started doing this weird ass like recursion, and like, it was like include the 0, and it was getting it wrong every time. And I was like, I know that the data I'm getting is good data. So what's happening? So that's I think the challenge with LLMs is it's not just to do hardware, is, you know, what's important in the data sheet. Okay, so that was the LM. And then, so there's like a lot of power stuff this week. I don't know. I'm in like a power mood. I think either somebody sent me or linked me to the TPS 61033. Now, the reason this is cool is we have in the shop the TPS 61023. This is a really popular little booster. Not just this board itself, but like we use this booster in a lot of designs. Anything that's USB. Anytime I'm like, oh man, I need 5 volts and like about a half an amp to an amp out. This chip is like 25 cents. And like the inductor, you know, I picked a good inductor that wasn't too expensive either. Doesn't need a lot of components, just like a resistor divider, enable pin, couple caps. It's really stable. It's nice and quiet, works great. It's, you know, like TI is really, they're on a roll with whatever this latest series. And so there's a new chip that TPS 61033. And this is, you know, this actually came out, I think in 22. I think I looked at the data sheet. So, you know, came out 22, but usually the data sheet predates the chip itself. So it came out, you know, 2 years ago. So it's not an old chip. It's a fairly new chip. And it comes in two versions. One's, you know, 1.2 amps. So it's about like 1 amp output-ish. And one is the 33, which has a 5.5 amp switch, which is a big improvement over the, I'm trying to remember the 23, 3.7 amps on the TPS 023. But, you know, it's like the 5.5, it's like, you know, 40%, it can give you 2 amps from a 3 volt output. It's kind of like what its range is. Built-in switches, you know, fairly efficient. It's like, yeah, like, you know, I always look at the, you know, when they talk about the efficiency, that's when they actually tell the truth about the capabilities. So yeah, 2 amps out from 3.3 volts, which means like a LiPo battery, or, you know, lithium ion, or like a lithium ferrite battery, about 3.3, 3.7 volt nominal, you could get out 2 amps, as long as, of course, you can source the, you know, whatever 3.5 amps out of the battery, right? The battery has to be able to do that capacity. Again, I really like the simplicity. You know, it's not only is it got internal switch, you know, internal boost switch, but it also has, it's synchronous, which means it has the built-in flywheel diode, right? Normally there would be a diode from here to the output that would act as, you know, the only forward current passing, and, you know, you'd pick your MBR, you know, 120 or whatever, but there is a forward drop associated with it. It physically takes up space. Also, it's a source of power loss, because you're losing that voltage, and it's not insignificant, especially if you're dealing with 2 amps. Like, you're going to lose half a volt. You know, that's 10% of your power through the diode. So I like that it had all that stuff built in. You know, there's a mode switch. You know, you can go for high efficiency or low efficiency depending on whether you're expecting high loads or low loads. Right? There's this whether it does PWM or pulse frequency modulated. You know, one is better for low current loads, one is better for high current loads. So I really like this. So I picked up the 3.3, not the 333, because this one has an output, and then I designed 2 boards with it. The first one, is a little bit like the bracket that we have in the shop. It's, you know, your breadboard friendly. Power comes in here. Oh wait, this got swapped. Whoa. Now I was moving stuff around. That's gonna bite me later if I don't watch out. Power comes in here through, you know, a very big inductor. Let me see if I can. Okay. Big 100 microfarad cap into the inductor, into the chip. You know, using a 2-ounce copper here. And then, you know, have a couple of, you know, 402 resistors. I had to go with 402 because I wanted to keep this ground path clear. You know, the routing starts to be very important once you get to this much current. You really want to make sure that you're following the data sheet. And the data sheet was like, look, you know, you're not going to have a direct top layer ground connect, but you should put a ton of vias right here. They're like, put the initial cap over, put the diodes, the vias here, and then you should have a shot, you know, from here underneath through the back plane. And then this is the output through 2 100 microfarad caps, and then 2 22 microfarad caps. And so that was like the first version. But then I was like, you know, I get asked a lot to make a Power Boost 2000, and I do have to go through and I have to like revise the Power Boost series because it's really ancient. Those chips are old. In fact, TI even told me, like, please revise these because people keep using these parts because they're in your Power Boost design, but they're like ancient. I'm like, yeah, I really fix them. So I might revise them to use this chip. I will have to add some other components though, because it doesn't have a low battery output. This has a power good, which is nice, but it doesn't have a low battery. So I'll have to figure out some comparator type thing that will tell me when the battery input drops below like 2 volts or something. Because people do like the low battery indicator. So this is a more power boost-y type design where we have the power coming in on terminal blocks into here, which is a nice smooth connection. Ground coming under here. There's a ground right underneath the VN, which I like. If you always want to have your return path as close as possible to your power path, the switch, and then the caps here, and then I put a little green LED here, and terminal blocks output. Terminal blocks, the reason I went with that is because I'm kind of into like, okay, you just plug things in together. Why not USB? I could always do another version, like I said, with the power boost like kind of design. The issue is the JST connectors we use on our batteries are not rated for 4 or 5 amps. Like they're perfect for the 2 amps, so I just copied what SparkFun did because I was like, well, they obviously know they have a standard and I want to maintain the standard. I'm into like whatever the community's doing. I try not to like come up with new breaking changes. I try to improve on the change, but I don't try to like break it. And so they use JST PHs, and JST PHs are like, I think they're rated for like 2, maybe 2.5 amps. So I had to go with terminal blocks. I got to figure it out. Also like the wires we have on our, because to get into the JST connector, the wires can't be too thick. So this is a little bit of a challenge. I don't know what I'm going to do. But for now, I'm like, you know what? I'll just design this and then we'll stick with it. Okay, how are we doing that time?
You're up to 17 minutes.
Okay, great. Let's go to the great search.
Where in the world is that part I need? The great search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit. Every single week, Ladyada uses her power of engineering to help you find the things that you want to find on digikey.com. Ladyada, what you looking for?
Okay, so this week we got a request for an LED sequin, and we stock LED sequins in the store. They're like little PCBs, and they have an LED and a resistor on them, and it's meant to like you could sew them very easily into clothing and costumes. And the request we had was, could you make one with UV LEDs? Because we stock them like so orange. We stock them with like red, yellow, green, blue, whatever, pink LEDs, but they wanted UV so that they could have this. They have like a flag or like a tissue, like a fabric tissue, and it is painted with UV-reactive paint, and they want to sew the LED onto the fabric itself, which I was like, that's kind of cool. So it would like glow like from within, kind of. And I thought that's a cool idea. So I thought, let's make a breakout for a UV LED. And then I was like, well, I have to go spec one. And UV LEDs, before you're like, we'll just pick whatever. But we have through-hole ones. But one thing to note about UV is it's actually kind of a wide spectral band. And it's used for a lot. So you have to be careful because UV can be as little as, there's the far UV, but basically about like 100 or 200 nanometers to the long, 100, which is ultraviolet C, which is like for germicidal, like, when people are like, oh, put your whatever glasses or jewelry into a UV sterilizer, it sterilizes it. That's usually shortwave UV. And then medium wave UV, which I don't actually know what people use for, but you can detect it. You have UV analysis, it comes from the sun. And then UVA, which is, about 360 nanometers. And it's once you get closer to 400, it becomes visible. That's like that purple light that you see from black lights. It's actually 400. As you get closer to 300, you can't visibly see it. You see UV light. There's always a little bit of leakage because that you're going to have a distribution of light that comes out. And so really like good UV LEDs, you're like, is it working? Because you see like a little, like they'll have a little faint, like purplish white glow to them, but it's because your eyes can't detect UV. So you have to be very careful around UV LEDs because you get like the really, really bright ones for curing resins and stuff. And you're like, is it on? And you could really blast your eyes. So just be careful with that. So the UV that we're looking for is, one second. No, so these are short wave, long wave. So black lights, right? So this is what they're talking about. They were like, we want a black light UV. Black lights are, they're often used in lamps because that's historically how we would get UV output. They're much less expensive, and they tend to do around 400-ish nanometers, is why you could see them and they look purple. They're also very bright. Problem is, of course, you don't want to wave around a glass wand when you're doing this, like, whatever performance dance. So what we want to do is find LEDs that emit, and I can look this up, 365. That's the nanometers that you want to get that will not be harmful to your eyeballs, but will make fluorescent stuff and dyes glow in a nice, beautiful effect. And also, of course, you want to get as close to the most effective frequency, because UV LEDs, and one thing you'll know if you use them is it's like you have to get like very bright ones to get a good effect, because again, they're not visible. You're reflecting the light off of this fluorescent dye and you're trying to get it to glow, and that's what you see. So you have to like really blast them. So if you're going to do it, and UV LEDs are not cheap, you might as well go for the best, closest possible frequency. What is this, like WinAmp? Who knows what this is? It's a weird like AI drawing. Okay. What's going on? Okay, so let's look for UV LED. And there's actually a couple. So one thing I'll say is that they have, for like the really beastie lights, you can get these that come on a heat sink. They're pre-made. We don't want these. They're also like kind of expensive. They're like, $12 is not too bad, but $40 is expensive. We're gonna make our own. But just so you know, if you want to like get a ready to go module, you can do that. There's UV reactive stuff, but we want LED emitters. Okay, and as usual, we're gonna look only at active. And let's just for now filter out marketplace, and we'll only look at normally stocking because we want stuff that we can buy. So that takes us down to like, 1,600 from 4,000. Okay, next up, obviously what we care about is we want it to be surface mount. There's a lot of through-hole UV LEDs. And I'm gonna get the dash as well in case. So that gets us 900. And then the next thing we want to do is make sure that wavelength, right? So we said 365. So some of these are much smaller. You'll see like 200, 270. They tend to be very narrow ranges. Let's just pick up 340 up to 390, maybe 400, just to see what's up. But we really do want 365, and then you see they get into like this very wide range. Okay, so that gives us 125 options. I would like to narrow it down to just 365, but we'll see what we got. Okay, next, we have a lot of options, but some of them are quite pricey, and that's fine. I get it. You need, this is like a 1.4 amp LED. This is like very, very bright. We're gonna try to not do that. See if we can get away with something that isn't. Again, a lot of these are used for curing resins or disinfection. So you need to like really blast the heck out of the area. Let's see if we can get away with something less. So let's search for, in quantity, 250, which is, about a quarter of a reel. And we sort. Okay, so the good news is that there's a lot of options under about $1. And another thing that's really nice is a lot of these actually, they even say that they are, 365, 395, 380. It looks like there's a couple options. So what I'm going to do is, since there are so many options within that 365 range, I'm going to get rid of the outliers, like the really high values, like 400 and 395 and stuff. This might take a while, 395. Could get reloads each time. That's okay. All right, now let's see what we got. So a couple of these, they don't have an image, but that's okay. These are, pretty big. Some of these have multiple diodes per LED. Some of these are really big. So the next thing I would do, the only thing that's a little annoying is they don't tell you the emitted light. You kind of have to just, you can look at the DC forward current, and that'll give you a good sense of like how bright you're expecting them to get. So this one is a good like high-end option. It's 250 milliamps. But since I'm going to make these little sequins, I'm going to just start with something simple. One thing that is nice, by the way, is they're almost all the same package, 3528. There's 0603. By the way, anything 0603 is not going to be very bright. It's tiny. Like you just can't put that much power through that size. So this is how big 3528 is, and then maybe just for comparison, I'll just show what 0805 or 0603. I think the resistor might be 0603. Let's see. 1 second. Okay, so this is 0603, just for comparison. So this is an 0603 LED, and this is, it's big, it's chunky, and they're expecting that there's a lot of current that's going to go through it. So that's kind of nice. So I thought I would start with this one because, it's 60 milliamps, which is, no joke. So it's like 2 diodes in parallel, probably, or it's like one very big diode that you can just put that much current through. 3.6 volts. It's expected, as you get to the shorter wavelengths, the shorter the wavelength, the higher the voltage. And it comes in at 3528. It's from Worth, which, they make really good stuff. And it's right at that right frequency, 365, and they've got lots in stock. So I'm going to try out this UV emitter and just emit, I'm just going to get the PCBs and I'm going to try a bunch of different LEDs and see which one looks best. Well, I'm going to get my CyberDog choker out and just see how it looks and compare them, and then we'll get them into the shop, whichever one looks best. So this is my UV LED pick of the week.
And that's a great search.
Where in the world is that part I need? The great search with DigiKey.
That's our show. Thanks so much for joining us.
Okay, thank you.
We got a lot of fun stuff this week. Yeah, we're doing stuff. We're hydrating.
Yes. Got some good tea.
Yeah.
Okay. Got some live shows this week.
Yeah, and if we can, because when we do videos with others, we have to just, hey, we did this video. Check it out before we post it. We're going to be posting, I think, the best and only interview with a C-level executive at a chip company with an actual engineer, Ladyada, asking questions.
He's also an engineer.
Well, yeah, but you're the engineer and you're the interviewer.
Yeah.
That's rare.
That is rare.
There's no...
And ask good questions, I think.
Yeah.
I think I keep it engineer focused.
I'm actually not as interested in who's being interviewed anymore as much as who's doing the interview, because they have to have good context. Like an engineer asking the COO of Microchip is way more interesting than whatever an analyst on CNBC.
Yeah.
Anyways, hopefully we'll be posting that video soon. We'll see everybody. Thanks for the support and more. We're going to go do some engineering.
Bye, everybody.
Bye.